Welcome to the Blue Waters webinar series. I'm Scott Lathrop at the National Center for Supercomputing Applications at the University of Illinois. I'm part of the Blue Waters team. It's my pleasure today to welcome you to a session on cinematic scientific visualization in Houdini. Our speakers today are Kalina Borkiewicz and AJ Christensen, and they are both with the Advanced Visualization Lab here at NCSA at the University of Illinois. It's a real pleasure to have both Kalina and AJ joining us today, and with that, I'll turn it over to you, Kalina.
Thank you for the introduction. My name is Kalina Borkiewicz. My colleague AJ Christensen and I are part of the Advanced Visualization Lab, or the AVL for short. This is an introductory webinar, so we're assuming no prior knowledge of scientific visualization or the software Houdini. If you have installed Houdini ahead of this tutorial and would like to follow along during the hands-on portion, you can download some of the content at tinyurl.com/Houdini webinar. I've posted the link in the Slack channel as well. But before we get into that portion, I'm gonna just take some time to define some vocabulary and introduce you to our team and our work. So the AVL is led by Dr. Donna Cox, who coined the term Renaissance team, with the belief that bringing together specialists of different diverse backgrounds makes a team that's greater than the sum of its parts. So we're a team of artists and programmers who work closely together with scientists to create cinematic scientific visualizations for public outreach. So I want to define how cinematic scientific visualization differs from some similar terms. The purpose of our work is public outreach, and we use Hollywood visual effects tools to create data-driven imagery that's aesthetically pleasing. This differs from typical scientific visualization, which is typically done for purposes of data analysis or for sharing results with other scientists or experts. And typically not much emphasis is placed on things like camera choreography or coloring or other aesthetic artistic elements. Scientific illustration, on the other hand, tends to be more cinematic but is not data-driven, and it's created by artists. And finally, information visualization is a different type of viz altogether, which is based on 2D data or data without spatial coordinates, such as networks or graphs. Our team has worked on many documentaries, IMAX films, planetarium dome shows. Here's just a few recent examples of that. And I'm going to show you some videos as just a sampling of our visualization work. So we work with a variety of sciences, ranging from geosciences to astrophysics to humanities. Cinematic scientific visualization provides another step beyond diagrams and abstractions that we're used to seeing in textbooks. The difference from those more simplified images is that it puts the science in context and is more emotional and memorable to audiences. Cinematic scientific visualization is an especially accessible form of science communication because it exploits the processing power of the visual cortex in the human brain, and because it leverages a powerful, familiar visual language established by Hollywood films. Similar to these Hollywood films, our work is often shown on giant immersive screens, such as IMAX and full dome theaters, with celebrity narrators like Benedict Cumberbatch and Jennifer Lawrence, who did a couple of our most recent films. Our visualizations are typically put in the context of a film with a human-centered narrative. Science stories often feature characters like galaxies or molecules, so it's important to remind the audience why they should care about these characters, to think about them in terms of the origins of life, threats to our safety, and human social systems. So that was just a little sizzle reel of some of our work. Now back to our slides. Just to give you some examples of the types of data that we've worked with recently. This is a simulation of a coronal mass ejection from our full dome show Solar Superstorms. which has implications for solar weather we experience here on Earth, which can affect communication systems and the power grid. The simulation had to be recalculated for our film because the pre-existing data that the scientist had wasn't saved out at a high enough frequency to be played back smoothly when put into film. This is a data set from the documentary Super Tornado, and this was based on a devastating storm cloud that hit El Reno, Oklahoma in 2011. This rendering relied on separate treatments for cloud, ice, and rain variables. And this is a visualization that's a work in progress from our dome show tentatively called The Birth of Planet Earth. We're incorporating VMD, a new to us biological rendering tool. We're incorporating that into our cinematic pipeline. What we're looking at here is a chromatophore, which is a simple photosynthetic organelle. This simulation was developed from a full atom-by-atom simulation on Blue Waters and Titan. And with that, I'll hand it over to AJ.
Thank you. So, you guys, I'm guessing a lot of the audience here is coming from the high-performance computing world, and so these pieces of software are things you're probably familiar with for scientific visualization. Visit, VMD, Vapor, these all sort of specialize in different data types. Some are more broad than others, and these are tools that we are certainly aware of and use on occasion. And I think actually Kalina is going to talk a little bit about YT especially being a part of what we do. But we focus more on a different set of tools. And these are sort of the Hollywood cinematic computer graphics tools. A lot of people who've worked with computer graphics are familiar with Maya and Blender as sort of two high-end 3D animation packages, and you may also be familiar with Nuke or After Effects as compositing tools. If you're not familiar with compositing tools, they are a pretty important part of our pipeline. You can sort of think about them as Photoshop for video. They're layered video, and it allows us to bring different elements into a single video. But our primary tool, really the one that we do a lot of development for and that we produce a lot of imagery with, is called Houdini, which is produced by a company called Side Effects. And this is the tool that I'm going to focus on today, and that you can follow along with. They do have a free downloadable version of this with a few limitations in terms of output imagery, which are that it will watermark your image, and it sort of limits your image resolution. But we do really love Houdini for a variety of reasons, and I guess I'll go ahead and talk about them while I play this video, which I think is a really good example of why Houdini is a really powerful tool. So this video is a reel produced by an advertising association. Doesn't appear to be playing. There we go. And it was produced with Houdini using motion capture data of dancers. And you can see in this that kind of the motion capture data is separated from the types of data. You can basically put all kinds of different data onto this motion capture data, and it's really flexible and it's really programmer friendly. Houdini is sort of unique from tools like Blender and Maya in the sense that it's highly procedural, and it preserves a history a lot better than these other tools. Everything's sort of built as a network of nodes, and so you can go back earlier in your node network and change a parameter very early on in your development pipeline, and that change will propagate through the network very efficiently. Houdini has lots of scripting interfaces. You can write lots of different types of shaders. There's ways to write code with Python. There's ways to write code with the native programming language HScript. You can write in a shading language called VEX. And one thing that Kalina does a lot of is developing a C++ plugin with a lot of different features as well. Another thing that's really important for us in choosing Houdini over these other tools is that it comes with a renderer called Mantra, which is really very high quality when rendering volumes, and when rendering volumes embedded inside of volumes, and when rendering geometry embedded inside of volumes, which comes up a lot in sort of the cinematic context Kalina was talking about, which may be less of a thing that you're used to seeing in sort of academic scientific visualization. Other sort of features that are really important are that Houdini is much more memory efficient than Maya. It interfaces with lots of other softwares and file types, and it has useful defaults and is just very well documented. So overall, Houdini has really turned out to be our preferred tool for cinematic scientific visualization. Some of the data types that Houdini can work with are triangular meshes, point clouds, volumes, image textures, and vector images. And it does these all very interchangeably. So you can kind of move from one type of data to the other very easily. It has it's got several renderers that you can use. It does realistic lighting. It has camera controls like depth of field and motion blur. These are a lot of features that aren't really included in scientific visualization software in the way that they are in cinematic computer graphics software. So, and I just wanted to share that Houdini to the scientific community may be less appealing than Blender because of its need for a license, but you can get fairly affordable educational licenses for it. And if you're trying to do things that don't require final imagery, you can actually even export geometry from the free version without any limitations. So it's pretty flexible, and even the free version gives you a lot of functionality. So this next slide is sort of about the paradigm, the way that Houdini works. Houdini is essentially operating around a big series of nested directories. And if you were to actually tear apart the Houdini scene files that you're working in, you would see that these nodes and networks are all just part of a nested hierarchy. So what they call sort of the top level of these are these sort of capital letter acronyms that may look confusing at first. So here in the graphic I have SOPs, ROPs, shops, and chops, and what those stand for are surface operators, rendering operators, shading operators, and channel operators. And there's a handful of other ops as well. But basically, when you enter the Houdini interface, you will see a variety of contexts that you can go into, and each of them allows you to work with either surface operators, which handle geometry, render operators, which handle output of geometry or output of imagery, shader operators, which handle the way that you put materials and textures onto surfaces and onto volumes, and channel operators, which bring in sort of series of data. And then inside of each of these contexts, you start dropping nodes. So a SOP node is a surface operator node. And inside that surface operator node is a series of parameters that describe, what a primitive sphere looks like, or describe, how you're transforming an object. And then I also included these sub-network folders, which are essentially just deeper hierarchies of SOP nodes. So you can have a SOP subnetwork inside the SOP context and then put SOP nodes in that subnetwork. Or you can put a subnetwork inside a subnetwork. And eventually, you end up with a very deep hierarchy of these folders. So that's kind of how Houdini organizes its data, which is a little bit different. I spent time on this because I want you to know that it's a little bit different. If you're familiar with Maya or Blender, it really helps to understand what's going on if you understand that. So I guess without further ado, I'm going to go ahead and just share some demos that I put together in Houdini, and you should be able to find these in the web page that we put together and have shared in various places. You can either download the individual files at the here link, or download a zip with all of the files at the link provided. So I'm going to start by opening the file called MOCAP Example. And this is going to load just a sample data set that actually comes packaged in Houdini. There's some motion capture human models that are just built in sort of to give you an idea of what Houdini is capable of doing with that data. And the first thing I'm going to do is go over here to this window over here, which is the node network editor. And up at the top, you can see that we're actually in this directory hierarchy right now. OBJ is sort of another term for the SOP context, the surface operator context. And so I'm just going to click that once, and that's going to bring me back to the top level. This is kind of where I intended to start, you guys, but the file saved funny, so it may open in the wrong place. So anyway, this is what is kind of the beginning point of any Houdini scene file. In the SOP context, or in the OBJ network, you can see that I have two things showing right now. I've got my MOCAP model, this human, and this blue flag on the right of the node determines whether it's visible or not. And then I've got tracking dots that are being traced and creating stream tubes here that I can turn on and off as well. So to give you a little bit more of a tour of the interface, above the node network is the parameter interface, and so that's telling you all the parameters that you can change about the model. So for instance, if I select the MOCAP model and go up to change parameters, I can change him from being a runner to being a jogger to being a sitter. So there's a bunch of things you can change there. You can change how fast he's moving. You can change what he looks like with this texture parameter. So these are all the things you can change about that. Obviously to the left is the 3D viewport, which you can move around just with your left mouse button. You can zoom in and out with your right mouse button. And with the middle mouse button, you can pan. If you get like way out of whack and you can't find your model, Shift-H will bring him back to the center. It'll center all the geometry in the viewport. And then above everything here, you have the shelf tools, which allow you to create geometry, modify geometry, add cameras and lights. And I just kind of will leave that as an exercise to the reader to peruse. And then there's sort of some various viewport manipulation tools over here on the right of the viewport. So if I wanted to change the type of lighting, I can click around. I don't actually have a light in this scene, so you're not seeing much change, but you can show and hide the construction grid. If you wanted to select an object, there's this arrow over on the left that allows you to choose a whole geometry, or if you wanted points, you click this tool over on the left and choose points. I'm not really going to get into any of this, and if you want to go back to camera tumble mode, you just hit the escape key. But so I'm just sharing some of this to kind of give you something to work with when you start exploring. And I would recommend in that web page that we put together, again, I'll point out there's a tutorial page that Side Effects, the company that makes Houdini, sponsors, and they're just sharing all the different good tutorials that people are making out on the web to understand all the many different deep crevices that Houdini has to offer. And then there's also another here link that has a series of MP4 videos, and this is the series of videos that I actually learned on 5 years ago. But so some of the interfaces are a little bit out of date because Houdini has obviously been updated since then, but it's a really well-structured sort of series of lessons that give you an idea of the things that you can do in Houdini. One of the things that I'm not even going to talk about today is dynamic simulation, so particle effects and volumetric effects. These are things that don't tend to come into play a lot in scientific visualization because the simulations are being done by scientific domain researchers, but you may find value in them at some point, and so I just want to make sure that you're aware of that. So just to kind of show how this scene is constructed, because stream tubes are kind of one of the things that we use a lot in scientific visualization. I'm gonna pull this scene a little bit apart. So just to create the motion capture guy, I'll show you. I should have mentioned there's this tab menu. If you click in the node network view and push the tab key, you'll have a whole menu show up with lots of different options for the types of nodes that you can create. And if you start typing MOCAP, you'll see a bunch of these choices pop up. And so this is how I created my motion capture character. Nothing special about that. And then the tracking dots example node is a little bit where the magic happens. So I'll actually point out when I dive inside the motion capture, the pre-made asset, there's I'll go ahead and make this larger. There we go. So you can see there's a lot of nodes here, and they're all sort of representing the different joints of the motion capture character. And so I've dived in here and found the sort of the wrists and the ankles because those are the guys that I really wanted to follow with the stream tubes. So so if I go back to the top level and then dive inside this tracking dot network, you'll see that there's sort of these 4 columns here. And these each represent the 4 tracking dots that I wanted to trace. And so I do that I trace them using an object merge node. That's a really useful node. That's the node that allows you to pull an asset from one network into another network. So we're kind of we're creating a bridge between the motion capture geometry network and this stream tube network. And so I'm grabbing these guys, I'm deleting geometry that is attached to them, and then giving them a color and merging them all together. So that's kind of what you're seeing here. And if I use this blue flag, that will visualize what's happening. So you're not seeing much right now because right now everything's just a point, which I can actually demonstrate if I hide this human. You can see these 4 little blue points. Those are my my tracking dots right now. Oh, and I can actually, here, I can make them bigger by just dropping some spheres onto them. So if I drag myself across the timeline now, you can see the character running, and he's got these spheres attached to his wrists and ankles. Kind of where the magic happens is in this trail node, which I'll go ahead and show you the parameters too above. This trail node basically gives you the opportunity to follow a point over time. So you can see as the guy runs through the scene, I'm dropping a little rainbow of dots behind him, and those are the past positions that his wrists and ankles have been in. And then I'll just add a line to it there with this node below it. The trail node, obviously, so like I was telling you earlier about the non-destructive history of Houdini, and I think this is a good place to demonstrate it. If I were to change the trail length from 20 to 10, I still have those lines, but now my history is half as long. I could make it twice as long as well. So it's a very flexible kind of construction. I guess doubling the length doesn't really help because he hasn't run that far. But anyway, so you can kind of see that, and then the nodes at the bottom of this network are just showing you the sort of the cleanup steps that I do. I convert it to a NURBS curve so that it's a bit smoother, and then I use this sweep method to put tubes on it. And then typically we like to end our networks with a null, and you might want to give it a name like outstream tubes. When you use capital letters in a null node, it makes it easier to dig through later. For instance, if you're using an object merge node like up here, and then you go searching through the hierarchy, the capitalized stuff shows up at the top there, as you can see. And I'll cancel that so I don't screw it up. So that's kind of just a really simple introduction to stream tubes and sort of a way to show off how Houdini deals with data. So I'm going to pop into another demonstration now, which is the one called Cloud Fun. So this one I built to sort of show the volumetric tools in Houdini, so that you can, I think it's pretty common to find volumetric formats for scientific data, and so this is one of the big selling points of Houdini. One of the reasons that we use Houdini so much is because it's so effective at working with volumes. So I'm not actually reading in any volume data at this point. That's something that Kalina will get to in a little bit. But just to kind of show what we can do with volumes, this first example, the Cloud Wrangle network, is kind of a really fun little thing, I guess. Here, I'll just show you. So I'm starting to make that cloud that you were looking at earlier with just a sphere node, and you can see that I've kind of stretched out a little bit, so it's just an ellipsoid. These mountain nodes are kind of a fun way to introduce procedural noise really easily. So my sphere now looks like kind of a lumpy cloud. Obviously still just triangulated geometry. Subdividing should be pretty straightforward. Kind of doing this alternating, subdividing, and mountain node operation is a way to come up with multiple levels of detail. And this is a really useful technique to use when you're trying to make something that stands up at different resolutions. And then this ISO offset node is another one of Houdini's sort of just magic nodes. It takes geometry and turns it into a volume. So you can now see this is sort of a uniform density. I've named my volume density, and I've given it a uniform resolution of 40 voxels across the max axis. So if you wanted to sort of understand what's going on in this volume a little bit better, one of the really neat features of Houdini is this middle mouse interface. So if you middle mouse button on the, oh, sorry, my laptop's a little flaky. If you middle mouse button on any node, it'll give you this little information dialog. And actually, as of Houdini 16, you can also just use this eye icon next to the node. Whoops. So if we look at this for a minute, you can see there is a volume called density. If I move, yeah, can't make this work. There's a volume called density down here. If you had multiple fields that were like density and temperature and metals and pressure and whatever, they would all be listed here, and they all show their volume resolution as well, and they tell you the exact number of voxels in that volume. You can also see how much memory the volume is taking up. There's just a lot of really valuable information. You can find your bounding box values here. So if you're ever trying to troubleshoot, that's a really helpful tool to do that. So moving on, I'm going to skip this one called volume wrangle and just go straight to volume slice. So volume slice is another really good diagnostic tool. It basically just puts a geometric plane right in the middle of your volume and shows you a cross-section of it. And you can change the range of that cross-section. So, I was previously at 0 to 4, now I'm at 0 to 1. I can also drag that plane backward and forward through the volume. And yeah, another really useful diagnostic tool, especially for people who are accustomed to working with data, is something called the geometry spreadsheet. So if I go up here above the 3D viewport, you can see this tab, geometry spreadsheet. And if I click on that, every point on the grid now tells me some information about itself. So I've got the position of each point. So you would expect like the PZ value on this grid for every point to be the same, and you'll see that that's true. The coloration that's coming from the data value is written here, and if I scroll down, you'll see how that kind of changes. And then the density value, this is the value that was actually written out by the ISO offset node, is shared here. And so you can see kind of most of the inside of that shape that I'd created is set to 1 by default. The edges sort of fall off right here in this range where you get the between 0 and 1 values, and then any voxel that's outside the shape that I created is set to 0. So if I go back to the scene view then, what we're going to do now is we're going to try and edit the volume a bit. Oops. Oh, and I'm going to throw out a disclaimer here. I pre-apologize if anyone's having like errors pop up when they open the Houdini files. The demo files were created in an older version of Houdini, and so if you just click OK past the errors, you'll be fine. There's nothing important in those errors, but there are a few little nuances that are strange. I'm currently working with a Houdini 15 file in Houdini 16, which is the most recent version of Houdini that you'll be downloading if you're just downloading it for the first time. So anyway, if I highlight this volume wrangle node, a wrangle, there are several types of wrangle node. In fact, if I pull up the tab menu and type wrangle, you'll see there's an attribute wrangle, point wrangle, primitive wrangle. These are all sort of slightly different contexts in which you can write code in this case, this is this VEX code that's a shader language that is native to Houdini, but is sort of a C-style language. So you can use these wrangles to write little sort of scripting edits to your data. And so you can do this to basically any surface operator, whether it's geometry, whether it's volume, etc. So I'll actually highlight this, get out of that volume slice, and another thing to know is this flag on the left, the yellow one, is a bypass flag. So it basically means operate without this node. So basically what this allows me to do is to toggle between the volume I had created previously and the volume that's being edited by the wrangle node. And you can see that the volume is changing a little bit. And the reason for that is that the equation that I wrote to edit it is creating sort of a radial fall off based on the distance of the voxel from the origin. And so this is why when I highlight the volume slice, you can see sort of a radial fall off inside the volume. And again, if I bypass the wrangle node, you can see now there's that uniform distribution in the density of the volume again. So and there's another example here in the wrangle. If I uncomment it, you'll see in this case I'm basically setting every voxel to the right of the y-axis to 0. So if I highlight the volume again, now you can see that I've basically chopped off a piece of the volume. So this is a really powerful tool to just do quick and easy edits to your volumetric data without having to do it externally. So then if I go back up to the object level here and go into the cloud remesh geometric network, this is just a little bit of information about playing with geometry and meshes, which some of you may have as part of your data. So again, I just have this sphere, mountain, subdivide, mountain business happening to create sort of this organic shape. Oops. Come on. And then I'm using this point node just to give it a color again. The point node has actually kind of fallen out of favor as a tool for editing point values, essentially. Essentially what everyone in the Houdini community is recommending now is just using a wrangle node and writing the code that says, the attribute that controls color is @C lowercase d. And so, you can see, like, if I create a wrangle, point wrangle, and say @cd equals, let's say, red, and then highlight that, I get kind of the same effect. The reason I'm using the point node here, though, is that I've actually got an expression in the color values. So this copy node here is another really fun, sort of unique piece of Houdini wisdom. It basically allows you to take a geometry and then instance it onto a point cloud. So what I'm doing here is I'm taking a line, and so I've actually made the line just points. So you can see here in this parameter interface, I'll actually hide the construction grid. So you can see that there's these 6 points here, and I'm going to use this point jitter node to kind of mix up where the points are. And then when I use this copy node, I drop that same cloud onto each of those 6 points into, sort of And you'll notice that these 6 clouds don't actually look the same, and that's because I'm using something called copy stamping, which allows me to slightly change the attributes of the cloud when I instance it. And so the values you can see that I'm changing here are the scale. I'm using these 2 offset values, and I'm creating an ID value just from the $PT means point number. So each of the points in the line has a point number 0 through 5, and that gives me a unique ID. So then you can see in this in the point node that I was talking about earlier, I've got this stamp expression that pulls in the ID and divides by 6. So these clouds should each be should have some red value between 0 and 1. And when you combine that with 1 for green and 1 for blue, you get sort of these varying levels from pure cyan to white. So that's why these clouds have the colors they do. And so you can see, like in the mountain node, I've put in these stamp value or stamp expressions to mix up the randomness that's being included. And even in the sphere at the beginning, I'm changing the scale of the clouds with another stamp expression. So anyway, the copy stamp node is a really cool tool that allows you to do a lot of really interesting organic effects, and this is something that we do a lot. If we get like point cloud data, we like to drop in, you can drop volumes onto those point clouds. You can drop spheres onto those point clouds. It's a way to sort of see different shapes on the point clouds and allow you to be a little bit more descriptive about what people are seeing. And those points could have arrows on them, which would actually, one of the copy stamp variables that you could include would be the orientation of that arrow. So each of the arrows might point in the direction of a velocity field, for instance. So then the other thing that we use a ton is a library called OpenVDB, which Kalina's going to talk a bit about. I just want it to be clear that OpenVDB is well integrated into the Houdini interface. So here, after I've created this sort of group of geometric clouds, I'm going to convert them to a VDB a VDB surface, which is made of voxels. One of the great things about VDB, and that distinguishes it from the native Houdini volume, is that it's adaptive. So it's, if you're familiar with adaptive mesh refinement, it's not quite as flexible as that, but it is more adaptive than sort of your standard uniform rectangular grid. It disposes the memory for voxels that are empty inside your bounding volume, essentially. So you're only storing information where you need it. You're still locked into a sort of uniform resolution, but you're not storing values where there isn't value to be stored. And the other thing that's really nice about the OpenVDB library is that it includes things like meshing. So if I use this convert VDB node, I'm converting that volume back into a polygon, but I can do it based on its I can create an isosurface based on the value in the volume. And obviously these volumes are all created with a uniform value with sort of a short fall off, which is why there's not much happening when I slide around in the ISO values. But if you were to import scientific data that had a really dynamic sort of range of volume values, you can just drag this ISO value around and get some really neat looking shapes very easily. So that's sort of a quick overview of that. And then the last demo that I want to share before I hand this back to Kalina is the scene file called moon.hipnc. And this is just sort of a quick example of importing external data into Houdini. There's a bunch of sort of ways to bring in external data into Houdini. Kalina's going to talk a bit about how you can use external scripting tools to do that. Some of the other ways that you can do it this example file is using an image file in a shader, but you can also bring in point clouds with a node called table import. I'll actually just show that off really quickly. So to create a new sort of SOP network, you just drop down a geometry node and dive inside it. Obviously, it starts by showing you this file node, which is the most straightforward way to import external data. You just need to make sure that it's a data format that Houdini is capable of reading. And Houdini has quite a few formats that it's capable of reading. It's got its own native format. It's capable of reading OBJs, STLs, PLYs. So that's always an option. But if you don't want that option, you can get rid of that. And this table import node here is a pretty powerful tool. So basically, if you have just sort of column formatted data, you can load that data file in here, and then just enter sort of the formatting of it with this column number and name tool. And then, and so like the name will create the name in Houdini. And I don't actually have an example file to show you this, but this is just a really easy way to pull a point cloud into Houdini. So anyway, I'll go ahead and show the actual idea here, which is using an image to create a displaced surface. So you can see this is a relatively straightforward looking network. It's only got 2 nodes, and the first is just a grid that we're going to displace. So if I just highlight that, you can see I made it fairly high resolution. I've got 457 rows and 590 columns, which is just a factor of the size, and the size is actually taken from the resolution of the image, which I think is actually 913 by 1180. And I'm actually going to point out in the files that you downloaded, we're actually working with this Moon Antoniadi crater image. So that's what we're looking at in the file over here. And so I literally just went into my into the Mac Finder and looked at the resolution of the image in order to get these values. And you'll actually notice too, any of the parameter values in Houdini can have sort of formulas or equations, expressions written into them, and that's really fun when you just like need to do some simple math and don't want to pull out a calculator. Here I've just written 913 divided by 2, and it immediately pops up with 457 because it rounds it to an integer. Another neat trick here with these expressions are I'm literally taking the 9.13 size x and dividing it by 2, and that is how I get the corner of the grid to be at the origin instead of having the grid be centered. And actually, I'll just quickly show you a trick for doing that really easily. If you right-click on this value, the 9.13, and say copy parameter, and then in a new field, say right-click and go to paste relative references, you'll see that it actually drops the expression needed for that right there automatically, which is really helpful if you don't really know the syntax of Houdini yet. So I'll reset that to 0. So all of the magic then is happening in this attribute VOP. So this is again using this VEX shading language that I sort of introduced in the Wrangle nodes, but it's now using something called a VOP, which is a VEX operator. And what VEX operators allow you to do is essentially write VEX code with nodes. So it's a visual programming language. And so this is a little bit more of an artist-friendly tool. If you're working with a designer, it's a tool that I think they will find a lot of value in. So I'll just go ahead and show you how I'm breaking down image file into sort of a displacement here. So if you create a new VOP, here I'll create a new VOP actually, and dive inside, you'll see that it always comes with these two, the geometry VOP globals and the geometry VOP output. And kind of the key there is that it always comes with a position value for both, and some other features that we're not going to bother with. So if you dive into the pre-created one, you'll see that I'm taking the position, splitting it into its parts, doing some operations to it, and then bringing it back together and spitting it into the pre-made VOP output node. So you can see that all I'm doing is really editing the Y value of the grid. And the way that I'm doing that is I am taking the X and Z values and dividing them by the total width and length of the grid, so that the values are now mapped between 0 and 1, which basically gives me a UV. It's not exactly a UV, but it's close. It's a similar concept. And I feed that into these S and T values of a texture node. And what I've done here is I've actually taken the map value, the map parameter on this texture node, and I've promoted it, which is to say that I've actually made it available at a higher level in the hierarchy. And so if you scroll down in the parameters here, you'll see that this texture map value has actually appeared at a higher level. And so you know, I'm just pointing it to the external JPEG file. You know, I could probably go out and find another image. How about bacon.jpg? So there you go. There's presumably an image of bacon that is now our displacement image. See if I can, yeah. Another neat little trick there, shift right click reverts a parameter value to its previous value. So anyway, that's where we pull in the JPEG. We use this texture node to do it. And then the output of that texture node is a color. And so then I'm converting the color from RGB. The texture node always creates an RGB color, so I'm converting it to an HSV, hue saturation value description of the color. And then when I split that HSV into its component parts and take the hue, I'm actually creating the depth now based on the hue of the image. And you remember that image was sort of rainbow colored, so there's lots of different hues. And I'm fitting that hue, which is originally from 0 to 1, between 0 and -0.33, and so that's how I get kind of the maximum depth of the displacement. So if I change this to like -3.33, you would see that I get a much more dramatic displacement. And so this is, you know, this is obviously a value that you can also pull from the data to make an accurate displacement height. And so yeah, so that's how I'm sort of creating this displaced geometry from an image. And I will throw out there that typically we wouldn't actually do this. We would actually use a material to do the displacement, because then you're getting a per pixel level accuracy instead of a per vertex level accuracy, which works a little bit better when you have cameras coming in close to features. You can get sort of an even better understanding. But the construction of a VOP in the surface operator context and in the shader operator context is actually very similar. You know, again, I'll leave that as an exercise to the reader, but this was just sort of an opportunity to show you a little bit of more about how you deal with geometry. So I think with that, I'll go ahead and hand this back off to Kalina now, who's going to talk a little bit more about coding tools that you can use externally.
Thank you, AJ. How do I get back to the presentation? Okay.
Yeah.
Okay, so AJ gave you an overview of Houdini, more how it's meant to be used without any custom plugins, just the way that it comes as is. But if you're working with your own data and you want to import that into Houdini, you're going to need to do a bit of programming. So there's a few different ways that you can get your data into Houdini. AJ described a couple of them already, but I'm going to focus on volumetric data. So one of those ways is by writing custom C++ plugins. If you Google getting data into Houdini, this will be the first result that you find. This is very well documented, and for many cases, it might actually be overkill. So writing a C++ plugin means that you create a node or some sort of element that fits directly into the Houdini user interface. So if you're then using Houdini, you can use the tab key, you can use sliders and parameters, and it works just like any other native Houdini element. So that's, very convenient for artistic purposes, but it's also, with all these sliders, it's great if you need to do a bit more than just reading in the data. For example, if you want to have more fine artistic control, you know that you'll be iterating, not just reading in the data once and then that's it, but you want to change things like resolution, spatial interpolation, temporal interpolation, any other fancy settings that you're going to want to code manually as well, then the C++ plugin is the way to go, because you can have all of those sliders and you can read in the data and do all of these different things to it while you're reading it. Some downsides of the C++ method is that it's a bit more programming intensive than some of the other solutions that I'll describe. If you're maybe not familiar with C++, you prefer Python or scripting, this may not be the approach for you. And something that's pretty annoying is that these plugins need to be updated with every Houdini version. And in my experience, that means that it breaks every year when we update Houdini. So that also might not be ideal for your purposes. So the second, perhaps easier, but a little less featured method you can do is scripting. And if you're scripting, you'll likely just want to run the script on your data one time to convert it into a Houdini-compatible format. I'll describe a couple of those formats. But then if you want to change things like the resolution or fall off or interpolation, you'll have to rerun your script manually rather than directly in Houdini, so it's kind of an extra step. And you can write these scripts externally, or you can actually code in Python directly inside of Houdini, because it comes with that. So you don't have to install anything else if you don't already have Python. So there's a few different ways to script. As AJ mentioned, you can write tiny little code snippets directly in the parameters, but you're probably not going to write a giant importing script that way. But this is a handy method. You can write these little mini script snippets in Python or in Houdini's language called HScript. You can create your own custom Python SOP. This is actually something you can do with a plugin, the C++ way or the Python way. So as AJ mentioned, a SOP is one of the Houdini elements. Like, it could be something as simple as a sphere or a cube. But if you create your own custom Python SOP, you can make this stuffed animal if you'd want to do that for some reason. Like I mentioned, you can code directly inside of Houdini. So you're going to need to convert your data into a Houdini-compatible format. And the simplest format of the Houdini ones, in my opinion, is a .geo file. That's because it's a text-based file, so you can actually open it up and take a look at what it is. Many of the other formats are in binary, so they're smaller and perhaps more efficient, but harder to debug for that reason. So let me briefly go over how a sample GEO volume file works. So you start off with a header. If we have a volume that's made up of two parts, a point that describes the center of the volume and then the volume itself. So you have one point and one primitive. You can have multiple points and multiple primitives inside a volume geometry file, but this is the simplest possible use case. If you have multiple points and volumes, you can group them together. They can have attributes, a lot of fancy settings, but we're not doing that in this example. So then you define the center point of the volume. In this case, we're setting it to XYZ of 0, 0, 0. And the fourth value, 1, is a multiplier. I pretty much always just set that at 1 so that it doesn't change the value, but if you're working with something that you want to multiply, you can do it that way. And then this line is the volume definition. This has a lot of settings that you probably will want to leave at defaults, but the main one that you'll want to change is these 3 values which define the XYZ resolution. Our sample volume is going to be a 2 by 2 by 2 volume. Just to explain what some of these other values are, this long string of numbers is a transformation matrix. In this case, we're just using the identity matrix, which means that we don't want to do any rotating or scaling or translating of the data, which you likely wouldn't want to do at this point in the data import phase, because that's something you could always do later inside the Houdini interface if you want to rotate your data, for example. These other settings, I've never in my experience worked with. I kind of leave them at the defaults. If you're interested in what they do, there is a file that comes with Houdini called gpd.txt that we've also included on the website with downloads that kind of describes what all of these things do. You can taper the volume, you can set values past the border, you can set how much compression is allowed, other stuff like that. Generally, I leave these just at the defaults. You probably will want to as well. And so here's our actual data. This is as defined in the resolution. It's a 2 by 2 by 2 grid, so there's 8 values there. And I'm alternating between 0s and 1s just to kind of show something a bit more interesting than having a single value. And then this is kind of how you end your file. You can put some extra settings in there, but we're not doing that. So I'll show you an example of actually reading that file in Houdini. So let's open up a new file. So I'm just going to create a file node using the tab menu that AJ described, and then I will, wait, actually I need to change my keyboard settings first. Sorry, I use a different keyboard layout than AJ, so so I can actually type on here. I'm gonna need to just change that. Okay. Back to Houdini. So I'm just finding the file now. There we go. So I set alternating 1s and 0s, so you see that half of it is filled in and the other half isn't. It's not very exciting, but this is, just a very simple example. Just that little bit of text created a sample volume. So right, okay, so that was some sample data. Now let's play with some real data. We're going to import this tornado data set. Here is the final visualization that we made of this tornado, but we're going to be working with a subset of this data that I've subsampled. And we're going to do programming directly inside of Houdini. This is something that you could do externally, but I just want to show off the fact that you can code in Houdini. So I'm just going to write a simple Python script. I went to Window and then Python source editor to open up this window. And now I can start coding. So I'm going to create a function called readTornado. And I know the resolution of my data, so I'm just going to set those values up front so I can refer to them later. And I know that each number has 4 bytes, so I'm just setting that value as well. I'm going to define where we want to write out our file. And then I'm going to open that file. I'm opening it with the W flag, which means I'm opening it for writing. For those not familiar with Python, I'm going to try to explain what I'm doing. The next step is setting up the header, which I've actually just copied and pasted because these are just kind of the default values that I glossed over that aren't that important. It would take a while to type out. But the important bit is that here I'm setting the resolution, like I said, so that's where these values are coming into play. So the next step is we want to read the actual data file. Yeah, and this header, well, this whole code is also provided in the downloads on the website, so you can copy that. So that's where our tornado data file lives, and we want to open that file now. This is a binary file, and we want to read it. So R is for read, B is for binary. That's how we do that. And now we want to write out the data values to this file that we are writing out. So we're going to do that by going through every value in the range. So for every point position, we're going to read that value from the data. And because this is binary data, we have to kind of unpack it using this command. And I'm using a library called struct that I need to actually import because that's not something that just comes with Python. So now we've read the value, and now we want to write that value out to our file. And then we have to end our output file with those begin extra and end extra words. Okay, so that's our entire reader. So this is a very simple data set, but we've written this script, and let's click apply and see if it gave any errors. It didn't. If I did do something incorrectly, let's just, I don't know, add some text here that doesn't make sense, and I clicked apply, it would print the error here. So then you could go back and see where that is. It gives you a line number, and so then you could try again. Now there's no errors. I can accept, and let me delete this previous one. So now I've created this function, and if I want to call it, I open up the Python shell. And here's how I can just call Python commands directly in Houdini. So that was something that was defined in this Houdini session. So to call it, you start with who.session, and then you see that read tornado shows up as one of the options. So if we do that, hopefully this will just take a couple seconds and will work, and we'll create a geometry file that we can then read. Hopefully any second now. There we go. So now that's finished, and I can go back here and use the tab menu to create a file node. And then I can go find my tornado data. So now it is loading that. And if I go here and press G, it will show the tornado. So here we go. We've loaded in this beautiful data set. So back to my slides. Okay, so that was one way of writing custom code. The third method that I want to talk to you about is something called Houdini, which is one of the latest software efforts of our group. It comes from the combination of YT and Houdini. By now you should know what Houdini is. Many of you may know YT, but if you don't, YT is a scientific analysis and visualization Python package. It's an open source tool that's been worked on by a lot of people over many years, so it's robust and it can read many different scientific data formats. And a realization that we had is that YT as a Python tool is something that we could use together with Houdini and its Python interface. And so what we have been doing is leveraging YT as a data reader, converting it into a Houdini-compatible format called OpenVDB, which AJ mentioned, and being able to read many formats that YT can already read without creating custom readers, and using those in Houdini without too much additional effort. So the example that I gave was a GEO file because that was something that you could read. It was text-based. OpenVDB is it's a binary file. It's a sparse volumetric format. It's a little bit more complicated, but you don't really have to worry about it too much if you're using YTini because we provide a lot of the code. But to give you a bit of a description of how OpenVDB works, it's with a regular volume, if we take this tornado data set, we have a value at every single XYZ position in this data, but there's actually a lot of zeros in this data. There's no values there, and this is actually taking up a lot of memory. All of these zero values take up just as much space as all of the actual values that we're interested in. OpenVDB is a bit smarter than that, and it actually is able to not waste memory on all of those zeros. It's sparse, and if your data is sparse or even partially so, this can save you a lot of time and memory. And this is the format that we usually work with our volumes. So, like I mentioned, YTini is a tool that we've created, and we created a website called ytini.com that has a lot of tutorials and downloads and examples and Python scripts. So if you are already a YT user or have data that you know YT can read, I strongly encourage you to check this out because it will simplify your data reading inside Houdini. And with that, back to AJ.
So, I think what I'm going to try and do here is actually build up a rendering on the fly. So I did include in the download a file called what's it called? Maybe I didn't include it.
Tornado render.
Oh, yeah, there you go. So tornado render.hipnc, which should have all of this stuff sort of pre-constructed for you. But just for the sake of seeing if I can have errors that I fix in real time so you can understand the debugging process, I'm going to just go ahead and create it from what Kalina has left up on my machine here.
You should change your keyboard.
Oh, sorry. And I will change my keyboard back to US. Let's see. Delete. Cool. Okay, now things will make sense, hopefully. So the first thing that I'm going to double check is that I want to know what the name of the volume is. And so again, that middle mouse button feature that I talked about earlier tells you that right now I have a volume called 0. And that's not a very meaningful name, so I'm actually going to start by giving it a new name with the name node. And I'm going to change the attribute name I'm actually going to rename it from 0 to density. Let's see if that worked. Didn't. I just do that. Oh, whoops. It's not a rename because it doesn't have a name. So you want the attribute that you're changing to be the name attribute. That gets kind of confusing because sometimes you just write density right there in the very first field, and that doesn't work. So anyway, I'm changing the name attribute to density. And so now if I middle mouse button on this, you'll see that there is a volume called density here. And also note that it's really important to have this blue flag on the final node in the network. And I'm actually going to make that final node in the network a null node with the name out volume, just so it's easier to find later. So now if I step out, I spent a lot of time in the OBJ SOP context, but there's actually several contexts which I sort of alluded to with my folders graphic, right? And you'll see that if you just do a single click on OBJ, you'll see that there's the CH context, which is the channel context, and the channel context is where you find chops or channel operators. The IMG context is the image context where you'll find COPs, which are composite operators. I don't know why they came up with different names for the context and the operators, so you kind of have to work your way through that. So OBJ is the surface operator SOP context. Out is the render operator or ROP context. Shop stays the same. Shop is the shop context. And then there's also a VEX context. So typically the contexts that we use the most are going to be the OBJ SOP, surface operator context, the shader context, and the rendering context. So OBJ, out, and shop are kind of the main ones. So I'm going to go to the out context now because that's what's going to create my image. And I'm going to create a new render operator called a mantra node. And when I drop that down, you'll see that this has all of the sort of rendering parameters that you would want in any rendering package. So you can change sort of the output image name. You can change the camera. So by default, it points to camera 1. It's not currently the scene doesn't have a camera, and so if I were to try and render this right now, so I'm going to do rendering in the render view. There's sort of several places you can do rendering, but I'm going to do the render view. You can see that I've now created this mantra 1 node, so that is the render operator that's going to try to render with. The camera that it's going to try and render with right now is called ROP camera, which is to say it's the camera pointed to by the render operator, which is cam1, which doesn't exist. So I think what's going to happen is when I click render, it's going to say, Oh, it looks like they've changed the default. So it's just going to pretend that there's a camera there where I think the scene view is right now. However, I'm going to suggest that you want to create your own camera. And so to do that, I'm going to, I'm actually first going to change which direction is up, because it looks like this data actually prefers Z to be the up direction. So I just did that in the Houdini preferences there. And now when I zoom in, I can kind of get like a nice close view of the tornado. And typically, you're looking at a tornado from pretty low on the ground. So I'm going to get nice and low. And then I'm going to go up to this shelf tool that's a camera icon. And if I hold down the control key and then left mouse click, it's going to automatically create a camera in the position that I'm at right now. So it puts me into sort of camera transformation mode automatically, which I don't find very useful. So I'm going to hit the escape key, and that's going to bring me back into tumble mode. And you'll see that as soon as I tumble, I'm no longer constrained in the camera view, but using this top right drop down, I can say restore camera 1. And if I want to move the camera while looking through the camera, this little lock icon on the right side here, this allows me to lock myself to the current camera so I can actually move the current camera. And so you'll see over in the render view now, it's automatically updating with my location. And it feels like I'm a bit close, so I'm actually going to zoom out a bit more. So now you're sort of starting to see the shape of this thing. So the other geometry that I'm going to want in my scene is just a ground plane so that I can cast shadows on it. So I'm going to hit the tab key and make a grid. And I'm going to make the grid a lot larger because it's obviously not very large right now. And I'm going to click that lock to get out of the camera view. So now we have this problem where the tornado is being split by the grid, and we don't like that. So I'm going to dive inside the tornado and transform it so that it is above the grid. And the way I'm going to do that is I'm going to attempt to remember the expression. Let's see, I want to move it up by half of the bounding box minimum. You know what? I don't know this off the top of my head, so I'm actually just going to fudge it for now, so you don't have to watch me Google the solution. Oh yeah, okay. So it's.
Why would be 220?
Oh, it's.
That's what you're trying to do.
Actually, and I can change this viewport too to look through orthographic views by holding down spacebar and hitting the number keys. So this is spacebar 3. And actually, you know, maybe the more obvious solution that you guys would be familiar with is just using the transform tools that most of these packages have. So I'll just do this for now. I'm sure there's a real solution in the pre-made file, but I don't want to make you wait for me to figure out what it is. So anyway, now we have the tornado above the ground plane. Yeah, so now so this isn't a super high resolution data set, which is good for the demo purposes so that we don't wait forever for things to load. But it's a little bit hard to see. The actual tornado funnel is just kind of this little feature right here. But I'm going to get the camera nice and close to that, and let's see how that's rendering. So one thing that you can see immediately is this sort of black bar at the bottom, and that is a problem caused by the camera clipping plane. And so if I select the camera and go into the View tab, I can change the near clipping to be much smaller, and you'll see that well, I guess I'll have to refresh the render, but the bar should go away now. Interestingly, the view also got really full of stuff. So I'm going to go and restore my key. Oh, right. Because I was not looking through the camera when I did that. So maybe now we have sort of a decent view. Okay, so anyway, now we have our camera, now we have our render operator node, the mantra node. Now we want to actually make this volume look like we want it to look instead of just sort of this default. And we're kind of lucky in that I've named the volume to density. If I had named the volume something else, it may not have even rendered. There's just sort of a default in Houdini to render the volume, the field called density. So kind of an easy way to build a volume shader, because volume shaders can be a little trickier than geometry shaders, I should say surface shaders. So we go to this material palette down here, which is another tab in the network view. And if I scroll down, I should find this billowy smoke volume shader, and I'm just going to drag that into the material palette here. It's just a pre-made volume shader that we've found is pretty useful for our purposes most of the time. it's built the same as any other shader. If I go back to the network view now, you can see it's automatically brought me into the material network view, and I can dive inside it, and it's made of nodes just like any other shader is. But all of the values that I care about are sort of exposed on the higher level, which is just sort of a convenience situation. So now you'll see that sort of the default is to read in a density field called density and to read in a temperature field called temperature, and do the opacity shading by the density field and do an emissive incandescence with the temperature field. There's also this noise tab that we tend to never use, and the OpenGL tab just sort of describes what the volume looks like in the interactive 3D viewport. Again, something that we don't really find we need to bother with. But you can do things here like change the smoke density, so I can multiply the smoke density to be 10 times more dense. And and it's not updating in the viewport because it's not actually linked yet. So I need to go back to the object context, choose my file, which I'm actually going to rename to Tornado. And I'm going to go up to this render tab of that geometry object. And you can see that the very first field here is material. And I'm going to go to the list and go to the material network and choose the billowy smoke shader that I just made. And now you should see things update. There we go. So now this is 10 times denser than it was before. And I'm going to throw out just a short note. Sometimes in previous versions of Houdini, this material network and the shop network were combined. They were the same thing, and they were both called shop. And so in the file I provided, you'll actually find a billowy smoke shader in the shop network instead of the material network. But in Houdini 16, it shows up in the material network. So now I'm going to interactively change it. So I'm going to take the density back down to 1. I'm going to make the density 0.1. So you can see that this interactive renderer updates in real time. I can also change the color of the smoke. I can make it a purple smoke or a red smoke. Typically, you think of clouds as white or gray. So honestly, leaving it at the defaults is probably pretty reasonable. So we still don't have a super dynamic image, which is in part due to the fact that I'm not a camera designer, so I haven't really picked a great viewpoint. But also, one of the most critically important things to making a cinematic image is lighting. So we really want to have some nice cinematic lighting in this. And some of you may have heard of the concept of like 3-point lighting, which is not always necessary, but the idea is that you have sort of a key light which highlights the foreground feature that you're trying to sort of draw attention to, and then you have a fill light and what's the background light? I kind of forget what the 3 are. So typically for us, what we'll do is we'll create sort of an environment light, and then we'll do sort of the third light is a backlight to sort of describe or fill out the edges of the geometry. So we'll usually use sort of an environment light to get the light everywhere, and then we'll use a key light to kind of highlight the thing we're looking at, and then we might have sort of a side light or a directional sunlight or some other kind of light just to sculpt out the 3D object. So in order to do that, I'll start with an environment light. You just use the tab menu and start typing environment, and what it will immediately do, I believe it should just start by lighting up the scene. Oh, except I haven't actually told it which environment to use. So I actually typically use an environment light that is just built into Houdini. You should be able to, in the left side of this file browser, see a directory that's called $HFS/Houdini/pic, and that is the default Houdini picture library. These are just some images that come with Houdini. And there's 3 in here that start with a capital DOSCH, and these are environment maps that just come with Houdini. And so just for argument's sake, we'll use Dosh skies. And now we should get an environment light to light up the view. One thing that I like to do with environment lights is use them as a background as well. And so I'm going to go to the parameters of the environment light and say render light geometry. And so that'll give us a little bit of a background to work with. I think it's way too bright right now, so I'm going to take it down to like 0.4 maybe. Yeah, 0.5. And so this is kind of giving us some nice ambient colored light on the tornado cloud as well. I think that the tornado is getting pretty light. It's a little bit hard to see, so I'm actually going to bring the density up so that it sort of blocks out the background more. So, and one other thing that is really helpful to understand how your opacity is working is if you switch to the alpha channel of the image. So I'm just toggling this with the A and C keys. So you can see that I've got like a fully opaque area here where it's all white, but I've got a fully transparent area here where the black is showing through. So that'll just kind of help you understand how your volumes will interact with the background. So then what I'm going to do is I'm going to create a key light the same way I created a camera. I'm going to surf around the viewport until I find kind of the place that I want my key light to be. So maybe like, I don't know, how about there? And then I'm going to hold down the control key and click point light. So now I have a point light right here. If I hit escape to go back into tumble mode and move away, you'll see that the light doesn't travel with me anymore, and I can actually look back and see where the light is. And now if I go back to the render view, you can see that there's sort of a really nice highlight on those clouds. It's also really important to make sure that anything that you want to render in the scene has this blue flag on. You'll see if I turn off the blue flag on the grid is just going to disappear. You kind of still see a grid because that's actually part of the environment light. But anyway, so make sure that anything you want to render has that blue flag on. And then I'm really hoping to see sort of a shadow being cast by this cloud. So I'm gonna get higher with the, oops, I gotta actually have camera 1 selected. And I'm gonna hit the lock button again to make sure that I'm moving with the camera. And I'm gonna get high enough that I can hopefully see some shadows being cast on the ground. Maybe too high. Not totally sure what I'm looking at there. Getting a little closer. So obviously, working with volumes, you can very quickly slow down your render times. It's nice though that Houdini has this feature with this progressive renderer, and you can actually, you probably seen me doing this, but when I hold down the left mouse button on sort of an area, that area finishes rendering first. So if there's sort of a feature that I want to resolve earlier than other features, I can do that. So this shadow question may not be worth waiting for, so I'm just gonna zoom out again and kind of get another wide view going. So one other thing that you could definitely do with the point light is change its colors. So if you wanted to have more of like a dusky sun color, you can kind of put in a little bit of orange. You can also go to the shadow value and change the shadow color to be a little bit more saturated. So so here now we've kind of got like an orange dusk light with a purple shadow, giving it a bit more sort of a shape. so you can create all kinds of lights. If I go to the parameters of this point light, you can see the type right now is a point light, but it could easily be a sunlight or a distant light or an area light. A lot of these lights take more time to render because they are a more distributed light source. But this is sort of where the process becomes a lot more artistic, and you want to just use a designer's eye toward what's going on. So I'm just going to go ahead and move on. There's sort of a little bit of a different setup in the file that I provided, but you can see here kind of the main way to do this. So I'm going to go back to the out context and look at this render operator again and show you just a few more things worth noting. In the rendering tab, I can enable depth of field and motion blur, which allow you to kind of have, again, more cinematic looks to your imagery, especially if you have a moving camera. These two things are super important. Although you have to take into account that it will be blurring your data, and as a scientific visualization person, you don't necessarily want to hide your data behind a blur either. So that's sort of a dichotomy that we work through a lot of the time. Below all that, all this sampling information is basically just telling you, if you're not getting a crisp enough image, it may be that you're not casting enough light rays through the scene, or you're not casting enough rays through the volumes, or some of the optimizations that are meant to make things faster are over-optimizing. So this is sort of a place to change the quality of your rendering. And the objects tab sort of allows you to change what's being rendered. Forced matte is a really useful tool if you're doing compositing and you want two things to fit together later when you're compositing them. Forced matte basically will render a geometry as a black hole in your image that you can drop other images into. And then candidate objects. There's sort of a little bit of a scripting language even here. Star basically means anything with a blue flag is a candidate object. I could put the star in force objects instead, and that would mean you must render everything with or without a blue flag. So again, these are just things to play with. One really sort of interesting feature is the extra image plane feature. If you, back in the images tab, there's sort of its own set of tabs, and you click on extra image planes, and I'm gonna check shading depth, PZ. And then you'll see, so there's actually a hidden toolbar here. If I click this, there's a little arrow here that I can show and hide that. And the default is to just show you the color channel, and you'll see when I hit the A, I guess it doesn't actually update, but okay, never mind that didn't work. But if I go to PZ, this is what I just added. This is the depth channel. So now things that are close to the camera are white, and things that are far from the camera are black. And this is basically a way to sort of cheaply create like an atmospheric fog effect, which again, our team has found is a really useful way to help people understand complex geometry by giving them a depth cue. So again, this is another tool that you can use in your compositing software to make the geometry more understandable. So I think that's kind of most of what I wanted to show off here. If you don't have anything else, I think we can go ahead and kind of call it a day. We do want to throw out there that we're always happy to take questions. The Slack channel is open right now, so if you have any questions for us while we're sitting here, we can answer those. You can also find our contact information on the AVL website, which I will pull up here at avl.ncsa.illinois.edu. And Yeah, so yeah, if you have any questions at all, please feel free to reach out to us. We're also actively maintaining ytini.com, and there are tutorials there. Ytini is a great new tool that we're using that we're encouraging other people to use as well, and we're happy to help you with in bringing scientific data into Houdini. Yeah. So otherwise, thanks a lot, and I guess will we leave the Slack channel open? Pass this off to Scott.
Yep, we'll leave the Slack channel open. If anyone has any questions, go ahead and post them. Or if anyone in the room has a question, feel free. While we're waiting for that, I always like to ask people how you learn more about the use of the tools, and it looks like you have good links to a lot of tutorials. Are there any you call out in particular, or just people have to sort through it themselves?
Yeah, well, let me show you where they are. Resources, tutorials, and files. There's one that I'm especially excited about that I want to call out for AMR data, which is a bit more complex than some other data types that we work with. For those not familiar, AMR is nested multi-resolution grids, which we've had a challenge with in the past because Houdini only works with uniform grids. But anyway, this tutorial tells you how to get AMR data into Houdini as well, providing code that you can just download or get more details about line by line. And yeah, so I encourage you to check that out. Hopefully it's detailed enough that you can follow along and get your own data rendered.
And just to sort of clarify, if anyone's looking to sort of get more involved with the features in Houdini, Side Effects, the company that makes Houdini, has a really great outreach effort. They work with a lot of professionals who are in the industry to produce these high quality tutorials, and they also will host their own webinars that sort of, especially when they release a new version of the software, they'll go through kind of a lot of the new features, and if there's any kind of paradigm shift, they'll try and explain that. And of course, just, you know, if you go to Houdini Help, there's a really thoroughly written documentation of Houdini. You can see there's this whole getting started section that talks about, you know, sort of how to understand Houdini. In the reference section, there's you know, H script commands, expression functions, Python scripting. VEX, again, is the scripting language in Houdini, or the shading language, I mean. And then if you're looking to do more of the C++ style development, I believe that's the Houdini Development Kit, which has its own documentation.
Yeah, and there's a whole section here called Getting Data In and Out of Houdini. So if you do want to go the C++ plugin route, this page has examples and more information about how to do that.
Okay, and one last question. I know it's a lot of work to create these visualizations. Do you have sort of a sense of how much time and effort using Houdini to produce some of these visualizations you've done, just to give people a sense of the level of effort?
So one thing that I think is definitely worth mentioning is, well, I think that the vast majority of the time that goes into a sequence, or maybe half the time that goes into it, is understanding the data, writing a data reader, dealing with the data externally before you ever bring it into Houdini. And you know, every scientist has their own format, and even within the same sort of field, there are different formats, and even within the same format, there's different versions of the same format. And so we actually, sort of as a proof of concept, created this render of a Milky Way galaxy simulation using the Ytini tool that Kalina has been working on, and basically took what has been a 2-month process and made it a 2-week process. It was, you know, it's definitely been a really great tool to bring the cinematic software together with the scientific software. I don't know if you want to be more specific or more general.
No, I think you answered that, but I kind of just want to call out, you know, you could spend as much time as you want. You can spend years making a single visualization, just improving it, you know, nonstop. I mean, AJ we just took, I don't know, half an hour and rendered a pretty good looking tornado. You know, you could keep iterating on that for days or weeks or months, and it'll get better and better, but you kind of just have to stop at some point. Depends on how much time you have and how much you, how cinematic you want it to be, for what purposes.
Yeah, the joke in computer graphics has always been, you know, if we improve the software and we improve the hardware, how long will each of your renders take? 20 minutes. You just optimize it for how patient you are, essentially.
Right. Okay, I don't think we have any more questions at this point, so please join me in thanking Kalina and AJ for a tremendous presentation. The next webinar coming up is on scientific software ecosystems by Lois Kerfman-McInnes and Michael Horo. That'll be November 8th. And then on November 29th, Jeff Carver will talk about software engineering practices. We will let all of you know when the final version of the video recording of this session is available, and we always welcome your feedback and recommendations for what we can do better going forward in the future, as well as additional topics you might like to hear about. So with that, we'll conclude today's webinar. Thank you for joining us.